Precalc chapter 4.1, this is exponential functions again. I know that we talked about this when we did our parent, family, child, and just to kind of show you guys that the parent, family, child works with a whole slew of different types of functions, and so it works with these. Here we're having a little bit more introduction again to what they are, because we're going to start getting into logs, and logs are just different, or the inverse of an exponent. So we're going to start off with an exponential function being f of x equals b to the x. This is different from what your book says. Your book wants to use a for a base. I didn't want to use a because in Algebra 2, in geotrig, you guys would have seen b used for base. It's a little bit more common that way. And so I changed it, say b to the x. Well, here's the thing. B to the x has everything that moves stripped away from it. So we're not moving it left, right, up, down, stretching, shrinking in any direction. Therefore, that's what we call a parent. And all these parents, guys, if you remember back to when we did this, y equals 0 is a horizontal asymptote. 0, 1 is the y-intercept. Why is 0, 1 the y-intercept? Because if I put 0 in for x, anything to the 0 power is 1. So therefore, that's why it works. What we would only need now is one extra point. Because remember, these were pretty easy to graph. All you needed was 3 pieces of information. An asymptote, an intercept, and then the one extra point on the tail. And I have that highlighted in red here. If it's growth, I'm going to pick a point like 1. If it's decay, I pick a point like -1 in for x. So growth, guys, remember, is when b is greater than 1. If you take something that's bigger than 1 and multiply it to itself over and over and over, you will end up with something larger. On the flip side, something less than 1, but still bigger than 0, so like a half, and you multiply it to itself over and over and over and over, you'll get smaller and smaller and smaller and smaller. So that's kind of something that you guys should understand. And so we have our asymptotes, y equals 0. We all have, both of them have 0, 1 as a y-intercept, and we have an extra point. So if you're given just a parent graph to graph, 3 points, not 3 points, but 3 critical things, done. Easy, fast. Okay? And so you just need those 3 points, and obviously we can start to transform this. There'll be an example of that using the parent, family, child. So when we start moving away from a parent, apply those things. Start at the parent, move away. Okay? Any questions? So the first thing we're going to do with our exponential functions is to write an exponential function. So if they give you a point that is on an exponential graph, can you write the exponential function? This is kind of like when we said, hey, x varies directly with y, or y varies directly with x. Can you write the equation? So the first thing I would do is write down what does an exponential function look like. Now we're sticking pretty simple here. They also gave you what the equation should be. So we should be looking at something like this for both of them. The question is, b. Do you have enough information to find b? What do you think we should do? Do you have an x? Do you have a y? Yeah, they gave you a point that's on that curve. So, in the first example, what's f of x? $25. What's x? 2. Now, if I wanted to solve for b, I would just take the square root. Now, most of the time, I've always been hounding at you guys to say, if I take the square root of both sides, solving for a variable, you must have plus or minus. In this case, we don't want plus or minus. We'll take the principal square root, or the positive one. B would have to equal 5. Guys, that's not the equation. The equation is f of x equals what? 5 to the x. It can be as simple as that. Now, why is it 5 to the x and not? So don't write this one. Why is it not that? Because we get both of those answers when you took the square root. Here's the problem. We want to have an exponential function. Let's think a little bit about what happens when a negative number is brought to a power. If I square this, the number is what? 25, and it's positive. If I bring it to the fourth power, the number is positive. 6 power, positive, positive, positive. But wait a minute. What happens when it's to the first power? It's negative. Third power, negative. Fifth power, and so on. So what happens, guys, the number obviously will get bigger, right? If I square this, bring it to the fourth power, sixth power, or the third power, or even the fifth power, the number itself gets larger, but the sign keeps waffling back and forth, yeah? And so what you end up having is this graph that starts off at 1 and goes up, down, back and forth, right? Getting larger and larger. Now, granted, that's not a really good graph. But it just keeps on expanding, but on both sides. Kind of builds like a little bit of a funnel. It almost looks kind of like a funnel on both sides. But you can't connect them that way. That's the thing. It's not a smooth, continuous curve. So therefore, it doesn't work. Okay? So don't do that. Guys, I'll give you guys a couple seconds here. Do the next problem. So what do we do? Yeah.
Can I do it okay?
Sure can. We're rolling right now.
Okay, so you want to plug 3 1/8 into this equation. So you get, oh, it's not a, oh, okay. Hey, I found the pen. 1/8 equals b to the third. And then we'll take the cube root of those. So you get 1/2 equals b.
Finish it.
Are you-
Done.
Oh, okay. So you go f of x equals 1/2 to the x.
Okay. So, right. Now, there's one thing that I'm going to actually add to this, just for comfortability. And that would be, I'm going to put parentheses around the 1/2. Because it's a fraction and you got an exponent on there, you just want to make sure that people understand it is 1/2 to the x power and not just 1 to the x over 2 or something like that, right? So that is correct. You guys come across problems like this, you're happy, you're not going to be too sad. So, also, problems like this, you shouldn't be too sad about. It's the letter E. The letter E or the number E. The number E is Euler's number. They say that potentially he calls it E because of exponent. Not sure. But the exponential function is e to the x. So guys, can you take your calculator out and evaluate e to the third power? E are 3 times e to the negative 0.25 power. And e to the 4.8 power. We're going to see some things going on here that might be slightly different. Notice that above I say e, you guys should have learned that in Algebra 2, that e is 2.71828. It's an irrational number, and we use the letter e for it, just like pi. So what is e to the third power? 20.06 la-di-da-di-da? It's not nice, is it? So you're going to have to approximate this. So if the book says, or the directions anywhere say to the 10th, you go to the 10th. If it's the Hundredths go to the hundredths. What about 3e to the negative 0.25? 2.34? That just got smaller. No? Oh. Now, this is where I wanted to put this on here, is because it matters what calculator you have, how you have to put it on your calculator. If you're using the old standard gray box or the computer to do this, you may have to do e to the negative 0.25 first, and then multiply it by 3. If you put 3 times e to the negative 0.25, your calculator just did 3 times e, and then took it to the negative 0.25 power. So, let's reevaluate this. Try everybody doing e to the negative 0.25 power, enter, multiply that by 3. What do you get? So now it's 4.1, 4.25, 4.16. Oh, I'm going to pause. I'm going to get my own calculator out here. Okay, we're going to go back with the original number here, guys. It is 2.34. Make sure that you put it on your calculator correctly. Hit enter before you multiply by 3. E to the... Hold on. Okay, e to the 4.8, sorry. 121.551 continues on, probably forever. So, it's important, guys, that you guys put it on your calculator correctly, but it's also important to recognize that why did all of a sudden the B one go smaller than e to the third power? Or why is that so much smaller? I understand it's 0.25, but it's negative there. Let's take a look at this, guys. Let's focus on the fact that if I say this is e to the negative x, what would you guys want to do? Yeah, it's 1 over e to the x. But what that doesn't recognize, I don't recognize that right there as an exponential function, because our exponential function, again, if I look back up to the top of this, is here, e to the x. So now isn't e to the x on the bottom? Nah, I don't like that. So wait a minute. That means this is also equal to something else. Would you guys agree that there's a power of a power thing going on right now? Isn't that negative 1 times x? So can't I split that up to say it's e to the negative 1 to the power of x? And then e to the negative 1 will go where? To the bottom. So you get 1 over e to the x. And since e is 2.718, 1 divided by a number bigger than 1 actually ends up in a what? Smaller number, less than 1. This, guys, now, here, you can see clearly that this will be an exponential decay problem. So, this is an exponential growth because this is e to the third power. That's 20. Your base number will be 20. This is 1 over e. That's 1 divided by 2.718. Therefore, it's less than 1. It's going to be decay. So, you have to kind of watch the way you do things. And the cool thing about this, guys, is that hopefully you start to recognize that when we have our exponential growth and decay graphs, you can actually graph like 4 different graphs and get the exact same, four different equations, and get the exact same graph. But so instead of stretching it horizontally and vertically, you can play with it this way and change the base number using exponent rules. So it's actually pretty cool. So let's use that idea of parent, family, child and making a sketch. we'll start off by giving you guys the parent. I'll give you guys some time to finish it off. What would the parent be for this? Parent is y equals, take away all moving parts, 3, 1, negative 1, and 2, right? What's left? E to the x. Question is this a growth or decay? Growth, because e is not positive, but this can be greater than 1, 2.718. Okay, so what things are we given for a parent exponential? 0, 1 is always there. What else? Y equals 0. And since it's growth, I'm going to pick up what kind of point? Growth is on what side? On the right side. Pick something close to home. These are exponential graphs. They get large very quickly. 1. And so when I put 1 in, I get e to the first power. I'm not even going to take the time right now to put that as a decimal. I'm going to leave it as e. I'll give you guys a couple seconds, a couple minutes here. Finish that out. Without going any further, you should be able to look at all the different transformational pieces, the A, H, and K. Tell me in words what's happening to it. Vertical stretch of 3. Right 1. Up 2. And by now, I'm hoping everybody would understand what you would do with each and every single one of those. We've been doing it over and over and over. So family, vertical stretch of 3. Y equals 3e to the x. Yeah? Our y-intercept, which was at 0, 1, now becomes 0, 3. Our y-asymptote is still 0, because if I multiply 0 by 3, it's still 0. And 1, comma, 3e. Again, I'm not even going to worry about decimals yet. I'll worry about that at the end. Child, we said, right 1 was it? Up 2? Y equals 3 to the e to the x minus 1 plus 2. The point becomes now what? 0, 3 becomes 1, 5. Y equals 2, because I'm going up 2. And the point 1, comma 3e becomes 2, comma 3e plus 2. At that point, I think I'm going to take the calculator out and figure out a value there. What would that value be? 4 point whatever e is.
Yeah, so like, no. Like, isn't e
2.718. You got to multiply that by 3 and then add 2. So it should be somewhere in the 20s, I'm thinking. Or close to it. No, 10. Sorry, 10. 10.2-ish. It's good enough. Just plot your data. Y equals 2, 1, 5, and 2, 10, 6, 7, 8, 9, 10, there. There's your graph. So it's not too bad, right? It's just using e instead of 2 or a 3 as a base. Same process.
Wait, the number
exponentials we are able to model a lot of things in the real world. Populations, money growth, all of those things deal mostly with populations. The more I have, the more I get, right? That type of thing. Depreciation. This one is about an infectious disease that begins to spread in a small town population of 10,000. After T days, the number of persons who have succumbed to the virus was modeled by the function. V of t equals 10,000 over 5 plus 1,245 e to the negative 0.97t. Questions? How many people were infected initially? Determine the number of infected people after 1 day, 2 days, and 5 days. And then graph the function and describe its behavior, probably using Desmos, because someone doesn't look like what we've seen so far. What do you mean initially? How do I figure out how many people were initially infected? Plug in 0 for t. The other class took over 10 minutes waiting for that answer. So, V of 0 will equal 10,000 over 5 plus 1,245 e to the negative 0.97 times 0. Anything times 0 is 0. So now you got e to the 0, which is 1. And 1 times 1,245 is 1,245 plus 5. And when we do that simplification, 8. So initially there were 8 people who were infected with this disease. You're like, not so bad. Yeah? Out of 10,000 people, 8 people are sick. How do I figure out at 1 day? Plug in 1. So V of 1, V of 2, and V of, not 3, but 5. I'm going to let you guys do that, and we'll come back together. So, on day 1 day out, there's about 21 people. Day 2, there's 54 people. Day 5 ends up having 678 people infected. Oh man, this is getting bad. CDC better be contacted. Guys, we're going to pause this, and we're going to go to the Desmos to talk about the end behavior. So the next thing we have is compound interest. Compound interest uses the equation A of t equals P times 1 plus R over N to the NT. P is the principal, R is the interest rate, A of t is the amount after t years, N is the number of times compound interest is compounded per year, and T is the number of years. The biggest thing is the more times that something is compounded or interest is compounded within a certain given amount of time with a fixed interest rate, the more money you will have, or more things that'll be there. So that's what we're trying to do here with this example here, is that if I have $1,000, keeping it consistent, keeping it at a consistent 12% interest rate per year, how much money will I have in 3 years if the interest is compounded annually, semi-annually, quarterly, monthly, and daily? The biggest thing you need to realize is that everything's all the same, except for N. So N, when annually, would be 1 time, semi-annually be 2 times, quarterly would be 4, monthly would be 12, and daily would be 365. Don't worry about leap year. So daily would be 365. So each one of these, you just change N. So what we'll do is we're just going to work with just quarterly. There's a little more space here, but every single one of these will work the same way. So A of t, for now, I'm going to leave the years out because I'm going to build a general formula. It says I'm going to put $1,000 in, and what I'm going to do is I'm going to add 1 plus the rate. The rate is 12%, but I can't use it as a percent. I have to use it as a decimal, over 4 because it's quarterly, and it becomes 4t. This equation here, and we'll clean it up, is the one that I would use to find out how much I would have after any amount of years that go by. And so to clean this up, it would be 1,000 times 0.12 divided by 4 is 0.03, so it would be 1.03 to the 4t. You can see this is going to be exponential growth because I have a base that's bigger than 1, but I also have a positive exponent, so I won't have to change it or kind of be a little worried about that negative being brought in with the power of power idea that we did in class. But that's a general equation. So if I want to know after 3 years, I just have to put a of 3, which is 1,000 times 1.03 times 4 times 3, which is 12. So I'm going to get a calculator out, and what we can do then is figure out what is 1.03 raised to the 12th power and multiply that by 1,000, and you end up with $1,425.77. In 3 years, you almost got half the amount of money for doing nothing other than letting it sit. That's the power of investing your money. Now, 12% is a pretty good return. So, I wouldn't expect that from most places, but it's really nice. It's easy to see, and that's how you do all of these. Now, here's the thing. There's another way we can do this, and that other way is what happens if it's compounded continuously. And if it's compounded continuously, they change things around and they bring in e. And so they actually use PERT, is what I like to call it, and it's a of t equals p times e to the rt. P is still the principal, r is the interest rate, and t is years. But we use e as a base. And so you can fill in the exact same way of a of t equals, notice this is the same amount of information, e to the 0.12t. A little bit easier on that, filling it in. And so now if I want to know a of 3, it'd be e to the 0.12 times 3. And when we put this onto a calculator, that ends up being 1433.33. Slightly different than what we got from first hour by quite a bit, but $1,425 or $1,433. You've got about $8 more in 3 years by doing it consistently or continually versus quarterly. So this is doing it more often. Now this is only 3 years. Make this over 60 years, it's going to even be a bigger difference. So the more times you compound your interest, the more money you will have. So your homework then is page 343, 310, 17 through 18, 23, 36, 44 through 45, and 51. Have a great day.